Hi, this is a video for task 3, telling a story. Today we are looking at a new concept, composite functions. Before we do that, let's record the definition of a function. We used to make the analogy of a function as compared to a machine. Right? For a function, you give me an input, I'll give you something back. You give me an x, I'll give you a y. So the function takes an input, performs some predictable, well, not always, but most of the time, performs some predictable operations on that input. Predictable because the function is probably in your closed form equation, right? So it's predictable, and it returns an output. Right? So you give me an x, I give you a y. So you can sort of think of functions as machines with inputs, operations, and output. Okay, you give me something, I'll do something on it, give you something back, right? Now, what if we have two machines working one after another? So we have one machine, another machine. This machine works first, then this machine. And we put them together, what would happen? This introduces the idea of composite functions. We have a function f and another function g. A composite function, it's simply a series of functions because we want one function to occur first, then another. Right? So a series. We call this series of operations a composite function. Composite function. Right. The above diagram can be represented by this notation, g of f(x), or we can write g, a little circle, then f of x. Okay, both representing the same thing. And this is easy to remember because you can just go from left to right and the order is the same. So we do g is sort of the outside function, and f of x is the inner function. Okay, so that means we do f first, then g. Okay. Let's consider this quotient example. So two functions, f of x equals 2x plus 1 and g of x equals x squared, performed in order. So we go f of x first, then g of x. So that is the output of f becomes the input of g. So whatever we obtain from f, we put it into g. Okay. So what will be the output of the new combined function if the initial output is x equals 4? Well, let's sub it into f first because we want to do f first. So f of 4 is 2 times by 4 plus 1, 9. All right. This is our new output. Now let's substitute this output into g. So we have g of 9 equals 9 squared equals 81. And that's our answer. So essentially we have g of f of x equals g of f of 4 equals g of 9 equals 81, right? This is essentially what we have. Now let me ask you this question. Is a composite function always valid? Do we always have composite functions? Do they always exist? No. The answer will be no. And the truth is that a composite function is only valid if the range of the inside function, the inner function, is a subset of the domain of the outside function. Okay. Why is this true? Let's have a look. So consider this function, composite function, g of f of x. So we all know that we do f first, then g. Yeah, that's what this means. And with this function, f goes from the set of real numbers to the set of real numbers, right? And is f of x equals x squared minus 1. the function g maps from this looks like the set of no negative numbers, no negative real numbers, to the set of real numbers. And the rule is square root of x. Okay. Let's have a look at the combination of the two. First of all, what's the range of f of x? What are the possible values that f of x can obtain, can produce? Well, this is a rule. This is a quadratic, right? But shifted y units down. So the minimum point will be -1. Right? And it's all positive because we have the x squared term. So every negative number becomes positive. So we actually going from -1 to infinity. Right? That's the range of f. What's the values? What's the range of values that g of x can accept? Yeah, what are the values that would g of x make sense? What's g of x? G of x is the square root. We all know that you can't take the square root of negative numbers. So g of x only makes sense for non-negative numbers. Yeah. So only if it's greater or equal to 0. Then can g of x accept everything that is produced by f of x? Can it? Well, g of x accepts non-negative numbers only. F of x produces -1 to infinity, which includes negative numbers. Yeah. So therefore, no, g of x cannot accept everything. Specifically, it cannot accept the subset -1 to 0. Hence, this function does not exist. Right? This composite function does not exist. Okay, let's look at a question. Consider this function f of x equals x squared minus 4 and g of x equals log of x. Define all their maximal domain. Say which of the following functions, f of g of x or g of f of x, is defined. And set the reason. Okay. So let's do it one by one. Let's first consider f of g of x. For this composite function, which one is performed first? G of x, right? Whatever is inside. Yeah. So g of x is performed first. So then the range of inside is the range of g, which is what? What's g? G is log of x. Well, log of x maps to the set of all real numbers. Okay. The range of g is the set of real numbers. And what's the maximal domain? So in other words, what is the possible values that f of x can accept? Maximal domain of f. What's that? We have a quadratic term, just shifted. So we can accept virtually all real numbers. So we are mapping from real numbers to real numbers. Oh, sorry. So real numbers fits into our domain, which is real numbers. Yeah. So therefore, the composite function exists. Right. So this function exists. Now let's look at another one. So the other one, g of f of x. So now, what's the range of inside? Range of inside is the range of f. What's the range of f? Well, f is a quadratic, shifted 4 units down, so it goes from -4 to infinity. Okay. What's the maximal domain of g? G is the outside function. So what's the maximal domain of g? We have a log of x. If you know well about logs, logs can only take values as positive. Okay. Because basically, the base e raised to any power is always positive. So x is always positive. So maximum domain of G is always positive. So it goes from 0 to infinity. 0 to infinity. Right? Now, let me ask you the question. Does this fit into this? No, because it has a negative part with it, right? This one goes from -4 to infinity. So it includes negative numbers, whereas we only accept positive numbers. So no, doesn't exist, right? So you can see that the order matters, right? The order of composite function matters. Even if you have the same functions, if you do it in different orders, one may not exist. Now let's look at domain of composite functions. What do you reckon is the domain of composite functions? So what's the domain of g of x, of f of x? What's the domain of that function? It will simply be the domain of the inside function. Why? Why is this true? Consider this function. Composite function g of f of x, right? G composite f. And let's suppose f is a function that maps from the set A to the set B. Okay? And G maps from the set B to the set C. My first question is, what do we first need to compute? What's the order? Do we do f of x first or g or the g first? F or g first? Okay, do f first, right? We do f of x first. Now, to be able to generate outputs from f, so in order for f of x to make sense, where can we choose our x from? What is the maximal domain of f of x? Well, it's stated here. We go from A to B. Okay. So now we know f of x makes sense. Okay, good. Now, provided that the output f of x is within the domain of G, in other words, this composite function exists, right? Provided that this is true, can we generate an output for g of f of x? Can we generate an output for the composite function? Yes, of course we can, right? Then, what are the values of x does g of f of x accepts? Right. Which means, what is the domain? Well, g of f of x only makes sense if f of x makes sense. Right? And when does f of x make sense? If we choose values from the set A. Yeah. So G composite F maps from the set A to the set C. A to B, B to C. So we're going from A to C. Sort of makes sense, I reckon. So let's look at question. Consider functions f of x equals to root x plus 4 and g of x, again, are quadratic, defined over their maximal domain. State the domain of the composite function g of f of x. What we need to do is we need to first check if the composite function exists. Okay. So what's the range of inside? That would equal to the range of f, which is what? Well, square root x plus 4 is defined whenever x plus 4 is non-negative. Yeah, we have a square root sign. So x plus 4 must be non-negative. So that's when x is greater than -4, greater or equal to -4. Okay. So when x is greater or equal to -4, this square root sign, this square root takes from 0 all the way to infinity. So range of f is 0 to infinity, and domain of f is minus 4 to infinity. Okay, now what's the maximal domain of G? That would equal to what? We have a quadratic term here. So essentially all real numbers. Real numbers. Does it fit? We have non-negative numbers and real numbers. Clearly that fits in. Yeah. So yes, exists. So G of f of x exists. Therefore, by our rule before, the domain is simply the domain of the inside function. So domain of G composite f is domain of f, which is just minus 4 to infinity. Minus 4 to infinity, right? Okay. Now, some people, you might ask the question, does that mean the range of a composite function must be the range of the outside function? Okay. The answer is no. Why is this not true? Well, because basically we cannot guarantee that the inside function makes everything that the outside function can take as inputs. So the composite function produces a range of values. The outside function also produces a range of values. But most likely, or not most likely, but sometimes you can't always get all the possible values that the outside function can obtain, right? Because you are not guaranteed that you have the full set for the as the domain for the outside function. Okay, we cannot guarantee that the inside function makes everything that the outside function can take as input. Maybe just half of those. So then we can only produce half of the outputs, right? Not all. So we cannot guarantee that the outside function will make everything that it can possibly make. Okay. So hence the range of a composite function is not necessarily the same as the range of the outside function. Right? In fact, the range of the composite function is a subset of the range of the outside function. Right? So it's always smaller or equal to than the range of the outside function. And they're only the same if the range of the inside function is the domain of the outside function. Okay. The range of the inside function, which will be the inputs for the outside function. If the range is the same as the domain, that means we have everything we needed. Okay. So only the same if the range equals to the domain. Then if range of f, or actually I'll just write inside, equals domain of outside. But in general, this is not true. Okay. And in fact, it is always a subset. So this is it for composite functions. End of recording 3.